Hello class, so today is about Gauss's law, conductors, and fields. So the objectives are to know Gauss's laws, or Gauss's law, we're going to really just focus on one. What is a Gaussian surface, to get your definitions down. Know how and what conductors are and how those work with electric fields, and then solve problem using these concepts. Alright, so Gauss's law in basic is the total of the electric flux. Remember, flux is the amount of stuff that goes through an area, in this case electric field, is equal to the charge enclosed divided by the permittivity. So, to write that as an equation, it's the electric flux is equal to the charge enclosed divided by the permittivity. This is just the permittivity constant, or epsilon naught. This is, I talked about it on my last video, but this is a number, and that's really all you need to know about. It's basically how well those electric fields go through things from a charge. So, as far as solving these problems, so a way to identify these problems is any time they say a charge is inside of something. Automatically, it's Gauss's law. So for this, always read through your problem. So it says you have a 3 coulomb charge inside a sphere of radius 5 meters. What is the flux? So we know this is our charge, this is your radius, but remember, always write out your law, which is the electric flux of an enclosed particle. This is enclosed, it's inside a sphere with permittivity. So if you read that, you realize, well, I don't even need to know the radius. This is unimportant information, meant to confuse you. You could go through and do the entire original equation, which, if you remember, is EA cosine theta, but you would end up getting the exact same thing anyway, and that is a heck of a lot more work to find all of the area on the outside of a sphere, so don't worry about it. So the moment you say, oh, that's something inside of something, Gauss's law. So all you would need to do is do your 3 coulomb charge over the 8.5 times 10 to the negative 12. If you're doing this on your calculator, really remember your parentheses. And that will give you 3.5 times 10 to the 11th power. Or again, if you're looking at your calculator, that could look like E11. So these questions are, while they sound difficult, are actually very easy to solve for. You just need to know what you're looking for. Alright, so next we want to talk about conductors. So conductors, hopefully you remember, they allow a charge to be transferred. So they allow charge transfers. And why this is important, it's important for our tools, but as far as the physics of the situation, if we have some sort of charge inside of a conductor, what is going to happen to that charge? So a couple main things. That charge is essentially made up by lots of tiny particles, so those things are not, the charge is not going to want to stay together. So the charge is going to spread out. Because of this, some funny things will happen. One of those being that there is no electric field inside a conductor. They do not exist. Alright, so to show you how this would look, so inside a charged particle, your charge is, a lot of times questions will ask you to show or indicate where the charge will be located. The charge, it's all positive. They don't want to be next to each other, so they're going to repel. I don't care how many you draw, the key thing is to draw them essentially spaced equally, or as equal as you can. I get if you have some challenge spatially separating things, those aren't perfect, but it's going to spread out as much as possible. Because it's spread out as much as possible, they are absolutely as far away as they can be. So because of this, remember we talked about electric field lines, and essentially alone a positive charge would give off these sort of fields outside, evenly spaced. But since, say if you put two positive charges together, they're going to go away from each other and then continue about their charging business. So on a sphere or a conductor like this, sure, they're still going to produce a charge, but since every direction but straight out is being covered by another positive charge, essentially your charges or your electric field is going to end up looking like this. So you could technically draw them curved out if you want to, but obviously this is getting a little tedious to draw. To abbreviate, we tend to just say we know it's all going out, so when you draw a equally spread out charged surface, I'm going to draw less this time, all you would say is that the charge is coming directly out, perpendicular to the surface. Because there is nowhere else to go, it definitely does not want to go inside. So all of your charges are going to be perpendicular to your surface, even if I didn't draw them well enough. And there is no electric field inside a conductor. So anytime it asks, like, oh, what's the electric field inside the conductor? There is none. Absolutely none. They're trying to make you do something. Don't do it. And whatever charge was inside is also going to be your charge outside. It's still 1 coulomb, it's just more spread out so it can be happier. So we're going to try a practice problem with that. Try it on your own, and then come back for the answer. Alright, so read over the problem, try it on your own, come back for the answer. Alright, now that you've had a chance to read on your own, main thing is always do read the problem first. A solid conductor with a radius of 2 centimeters has a charge of Q equals -7 coulombs on its surface. So draw the electric field lines. B, find the electric field 1 centimeter above the surface, and C, find the electric field 1 centimeter inside the conductor. Alright, so first off, it's always good, draw a picture. So we have some solid conductor. I like to always assume it's a sphere. Otherwise, don't worry about it. It's not going to be that important. And, you have 107, or -7 coulombs. Alright, and first thing is draw the electric field lines. So you know, and also because your problem helps it by saying it, that its negative charge is distributed on the surface. And because of that, the electric field lines are not anywhere but outside. And since they are negative, it is going in. Remember, main thing is just try to draw them as evenly as possible. I drew 7 charges because it said -7. You don't really have to, as long as it's evenly distributed. Alright, so that's the first part. Next, find the electric field 1 centimeter above the surface. So if you didn't go back and look at your formulas in your packet, this might have been more difficult, but there are 2 formulas that you might find useful. One is that the electric field is equal to the force electric over your charge, or that the absolute value of your electric field is equal to KQ over R squared. And in this case, that is going to be the one you want. So we're thinking about which one is more effective. Think about what we already know. We don't already know the force, so this is not a terribly helpful equation for us. But we do know the charge, we do know our radius, and we do know that K is always 9 times 10 to the 9th. So we are going to want to use this equation. A key point is your radius should be in meters. 2 centimeters is not in meters. So you want to take your 2 centimeters and convert it into meters by moving it over 2 times. So it's 0.02 meters. Alright, now we can use that to solve. So this is equal to k, which is 9 times 10 to the 9th, times our q, which is a -7, divided by our radius squared, so it's 0.02 squared. If you do that, you'll get the answer as -1.5, or I'm going to round that actually, -1.6, excuse me, times 10 to the 14th. Alright, and one last problem, as I've noticed that today we've been having an issue with it, and I'll be back. Alright, so in case you don't remember, this was number 4 from today in class. So when you are doing this problem, first think, okay, it is an enclosed charge. So since it is enclosed charge, we are most likely going to in some way use this equation. So first things first, do part A. It says draw the field lines. Remember, there is no electric field inside your conductor. So your electric field would start outside. It is a positive charge. So you would have positive lines going outward. Alright, and then you want to actually find the electric field. So to find the electric field, well, there's no clear ones. But we can, however, find the flux using this equation. If we find the flux, we can then go back and use this equation to find the electric field. So this is actually what we're going to do. So some things to know: that the area of a sphere is 4 pi r squared, and that the degrees for it is 360 because it's a full sphere everywhere. Alright, so if you haven't yet tried it, please try it. Otherwise, follow along. So first off, we need to find our flux. So to find our flux, we can put our q. Oh, and excuse me, our radius here is 2 meters. Or, yeah, 2 meters away. So to find that, we first have to find your flux. So your Q is 8c. Your epsilon is always 8.85 times 10 to the -12th. If you do that, your flux is going to be essentially 9 times 10 to the 11th. Alright, and then we can go back and say, plug this in to your flux equation. So it's 9 times 10 to the 11th equals our electric field. Remember, this is what we wanted to find. Times our area times cosine of theta. So to get our electric field alone, divide by your A cosine theta. This crosses them out on this side, so you can just essentially get rid of them. So you can see that E is equal to the flux divided by A cosine of theta. And then you can plug in. So your A is going to be your 4 pi. Your radius is 2, so 2 squared, times your cosine of 360 over 9 times 10 to the 11th. Alright, this would end up being 16 pi. Cosine of 30 is just 1, so again, we don't really care. So it becomes this divided by cosine of 9 times 10 to the 11th divided by 16 pi. And it's going to give you 1.798. So if you round it, you will get 1.8 times 10 to the negative 10th. Alright, hopefully this is helpful. Sorry it was a little long, and I will see you tomorrow. Remember, tomorrow, go to the library. We are in the library tomorrow. Make sure your rough draft is turned in. So if you have not already turned it in, make sure you turn it in. Check on turnitin.com because I've had a lot of people say they turned it in, but I have never received it. So please make sure that happens.